Good morning. Today I am going to teach fundamentals of mass transfer. In it, our main focus will be to learn on the topic of diffusion. Now, first I'll give a brief introduction on the fundamentals of mass transfer. Now, we have already learnt what is heat transfer, and we know that heat transfer is due to a temperature difference in the medium. Drawing analogy from that, if there is a difference in concentration of some species in a mixture, then mass transfer will occur. Hence, we can say that if heat transfer is occurring due to the driving force of temperature gradient, mass transfer will occur due to the driving force, which is the concentration gradient in the mixture. Consider a basic example of dissolution of potassium permanganate in water. Now, as soon as we drop the potassium permanganate in water, very near the crystal there will be a dark purple zone, and the concentration is high over there, and because of the concentration gradient established between the region near the KMnO4 crystal and region far away, there will be diffusion of the KMnO4 crystal, KMnO4 away from the crystal. So, this illustrates the example of mass transfer. Now, under mass transfer there are two main classification: diffusional mass transfer and convective mass transfer. Now, diffusional mass transfer, as you can see, it is due to the movement of individual molecules through a fluid or solid by means of random individual movement of molecules due to their thermal energy. And now a molecule is imagined to travel at a uniform velocity until it collides with another molecule, and the average distance which it travels is the mean free path. But since the molecule travels in a very zigzag path, the time taken to travel the net distance is high, and hence the rate of diffusion is very slow. So, under diffusion, we will basically learn what are the applications of diffusion, the basic mechanism of diffusion, the rate of diffusion given by Fick's first law, and the factors affecting diffusion. Now, first let us see certain applications of diffusion, like furnace for heat treating steel using carburization. Carburizing is basically the addition of carbon to the surface of low carbon steels at this temperature range, and hardening is achieved when a high carbon case with good wear and fatigue resistance is superimposed on a tough low carbon steel core. So, and in chemical engineering applications, this was more of a metallurgical application. In chemical engineering application, you will find this application of diffusion when there is absorption of a gas in a liquid. When there is absorption of a gas from a mixture of gases into a liquid. So, basically diffusion is a consequence of the thermal motion of atoms, molecules and particles that results in material moving from high concentration zone to low concentration zone, and basic mechanism is seemingly the Brownian motion, which is the random movement of particles suspended in liquid or gas. Now, how do we quantify this rate of diffusion? It is given by the flux, which is nothing but the moles diffusing per unit surface area per unit time. So, this is denoted by J, and J is nothing but 1 by A dm dt. Here this m can be mass or it can be moles diffused, and accordingly the unit of flux is moles per centimeter square second or meter square second, and kg per meter square second, depending on whether it is molar flux or mass flux. So, now consider steady state diffusion across a thin plate. Steady state means the rate of diffusion is independent of time. That is, the flux does not change with time. So, in the left hand side we see the actual process, that is the gas on the left hand side of the slab is maintained at a pressure PA, and on the right hand side the gas is at a partial pressure PB, and the gas is diffusing through a thin metal plate, and PA is obviously has to be greater than PB in order for that the gas diffuses through the plate. So the concentration of the diffusing species, the concentration profile of the diffusing species with respect to position is given in the on the right hand side, that is this diagram, and concentration and rate of change of concentration with respect to position, that is the concentration gradient. So coming back to steady state diffusion, we can state that flux is proportional to concentration gradient, that is dc dx. Hence Fick's first law of diffusion can be derived, which is J equal to minus d dc dx, where d is the diffusion coefficient or diffusivity of a gas through another gas or through a binary mixture. So if it is a linear concentration profile, then dc dx can be written as del c by del x, which is equal to c2 minus c1 by x2 minus x1. Now about this negative sign in Fick's law comes because the component is diffusing from a region of high concentration to a region of low concentration. Hence C2 is less than C1, and hence for the flux to be positive we have to adjust it by a negative sign. Just in case of Fourier's law we have seen that minus k dt dx. So this is a given data of d c1 c2 x2 minus x1, and a flux can be simply calculated using this formula. But one thing is to be noted, that Fick's law of diffusion is applicable only for steady state diffusion. Fick's first law of diffusion can be applied only for steady state diffusion. Now this diffusivity or diffusion coefficient is a function of temperature, which is given by relation, an exponential relation, d equal to d0 exponential minus qd by RT, where qd is called the activation energy and T is the absolute temperature. Activation energy is the energy required to produce the movement of 1 mole of atoms by diffusion. So there are several cases of diffusion, of molecular diffusion. Diffusion takes place basically in molecular level. So one case that I would like to discuss is steady state diffusion of A through non-diffusing B. This is the case which is which happens industrially when a gas when a particular gas present in a binary gas mixture is being absorbed by a liquid. So say for example CO2 and air mixture, or ammonia air mixture, where ammonia is being absorbed by water and air is the non-diffusing component. So in that particular case, applying Fick's law, we obtain the expression for flux as Na equal to dAb Pt by RTZ into Pa1 minus Pa2 divided by PBM, where PBM is the log mean pressure difference. Now this equation is depicted graphically. So whenever a gas is diffusing through another stagnant gas, the concentration profile or the partial pressure profile versus distance is as follows. This is a PBM comprises of a logarithmic term, hence this is a non-linear type of graphical representation. And when there is steady state equimolal counter diffusion, that is the situation which occurs in distillation operation, there both the gases are diffusing but in opposite directions, and there the profile generated will be like this. The pressure versus distance profile generated will be like this. So this is the basic principle of diffusion, which has wide range of industrial applications, and a governing equation will be the Fick's first law of steady state diffusion. Thank you.